We introduced the idea of exceptions to the octet rule in the last set of problems, and obviously in the notes. So these are just some examples. So BH3, we've got 3 valence electrons from the borons. Each hydrogen has 1. There's no way to draw it and connect everything other than this. There's no double or triple bonds that could be put together to fulfill octets for everything. And boron, because it has a fairly low electronegativity and a low Zeph, is often as stable as it can be with this. We'll see, or you would see if you go into a more advanced chemistry class in college, when you get into the Lewis theory of acids and bases, how boron often does want to accept a lone pair from something else or bond with something, but from a single molecule sense, this is as stable as our boron can be. Here on part B, we have ClO2, and it's not ClO2 minus. It's not the chlorite ion. It is chlorine dioxide. So when we add that up, we see that it's 7 plus 6 plus 6. We have an odd number of electrons. There's no way to pair everything up or to complete all of the octets with an odd number. The first thing you would do would be double check. Is there an ion charge that I missed? There's not. So then we draw our structure. We follow the rules the way we normally would. Single bond, set of 6 electrons, set of 6 electrons. And then there are 3 electrons that haven't been used. We place those on the central atom. We could then move electrons in to see what happens there. This one might experience a little bit of resonance. Chlorine could expand its octet, and the oxygen, by double bonding, would go to a formal charge of 0. But just know that no matter what we do, chlorine's going to end up with an odd number. So this works. We might see some resonance. We might then use our formal charge to confirm which one's the best. But it's important that no matter what we do, that chlorine's going to have an odd number. Right here we have arsenic pentafluoride. Arsenic is in row 4 on the periodic table. That means it has at least 4 energy levels, not at least, it has 4 energy levels worth of electrons. As an atom, it is large enough that not only can it hold 8 electrons, it can hold more. So this is the really best and probably only structure that would make sense for this one. The fluorides are each full. When we add up our electrons, we've got 7 for each fluorine, 5 for the arsenic. We add all of those up, and this is a good structure here. Anytime we would move things in to make a double bond, that would give arsenic more electrons than it wants from formal charge while taking them away from fluorine. So less likely. Arsenic and phosphorus are likely to be able to form 5 bonds, and sulfur, selenium, tellurium, that column, once you get far enough down in a large enough atom, can form or hold 6 electrons and have 6 bonds. And we saw that with sulfate and even SO2. This last one, we've got xenon tetraoxide or tetroxide. We think of noble gases as not wanting or needing to bond, but sometimes they'll bond with the most electronegative elements, fluorine, chlorine, or oxygen. Those 3 elements need more electrons and attract them very strongly. So an oxygen is unlikely to be stable by itself, but by sharing electrons with something, it becomes more stable. When we do this, we follow the rules. We connect with single bonds, we fill with dots, and then we get to using the right number of electrons. When we are doing that, it's very important that we count them. We can put our extra dots on our central atom of xenon. Xenon is very far down on the periodic table. It's in period 5, so it could hold 8 or more, a large enough atom with a high enough Zeph of 8 to attract those additional electrons in. But we have to make sure that we're using the right number of electrons. So we'd have 24 plus 8, it should have 32. This uses 32 here. As we look at this one, we actually have too many electrons. So I'm going to kind of highlight that in a ring of red to show that it's not totally correct. I'm going to highlight this guy in a ring of green to show that that one's the better one. But I did want to show, I included this to say that, yes, you can have lone pairs on a central atom, even when that takes that beyond the 8. So you could have bonds that take it beyond 8 or lone pairs that take it beyond 8. So right here, we actually have too many electrons, or more electrons than the oxygen and the xenon brought to the party. There's some arguments as to whether this would be possible and good, where some of the D electrons would get involved. That's beyond what we would need to know. This is more just an example of you can have single bonds and dots, or you can end up with multiple bonds, and the formal charge is our indicator as to which is better. Here, our oxygens have what they want, 2 sets of dots and 2 bonds. There, we would have formal charges all over the place that would throw this off.